Today in Math 20-1, we're going to look at topic 1.3 on geometric sequences. In a geometric sequence, for example, 3, 9, 27, 81, the ratio of consecutive terms is going to be constant. That means the common ratio, r, that can be found by taking any term and dividing it by its previous term. Or term 2 divided by term 1, 9 divided by 3, gives me a common ratio of 3. Notice that 3 times 3 is 9, times 3 is 27, times 3 is 81. So our common ratio is said to be 3. The general geometric sequence is term 1 times that common ratio, and then term 1 times the common ratio squared, and then term 1 times the common ratio cubed, all the way, keep going, where T1 is the first term, and r, of course, is the common ratio. This continues the pattern all the way down to Tn, the general term or the last term, which is Tn is equal to the first term, T1, times r to the power of n minus 1, one less than the term that we're looking for. So there you have it. The general term of a geometric sequence, when n is a positive integer, is T of n is equal to T1 times r to the power of n minus 1. Let's do an example 1. Determine the first term, the common ratio, and T of n. In this example, it's said that in nature many single-celled organisms, such as bacteria, reproduce by splitting into 2, so that one cell gives rise to 2, then 4, and then 8, and so on, producing a geometric sequence. Suppose there were 10 bacteria originally present. That would be our term 1. That means that term 2 would have to be 20. Suppose there were 10 bacteria originally present. Determine the general term that relates the number of bacteria to the doubling period of the bacteria. State the values of T1 and r in the geometric sequence produced. Well, now that we know what term 1 and term 2 are, we can divide those two and get the common ratio. And that's going to be 2. Now, Tn, there's our sequence. Tn is going to be T1 times r to the power of n minus 1. So we're going to say that Tn is going to equal our first term 10 times our common ratio 2 to the power of n minus 1. And that's it. That's all there is to it. Now if we went on and asked what's the 9th term in this sequence, I'm going to show you how this works. We're going to say T9, T of 9, is 10 times 2 to the power of n minus 1, and 9 minus 1 is 8. So that's simply going to be 2,560. Your turn, we can let you work on by yourself, but there's the answer. In the second example, determine a particular term. Sometimes you use a photocopier to create enlargements or reductions. Suppose the actual length of a photograph is 25 centimeters, and the smallest size that the copier can make is 67% of the original. What is the shortest possible length of the photograph after 5 reductions? Express your answer to the nearest tenth of a centimeter. Well, our term 1 is our starting point, and T1 is 25. Now, our common ratio is going to be 67% of what it was previously. Expressed as a decimal is going to be 0.67. So, what do I know? I know that there's going to be 5 reductions, so n must be 6. That's because our first term is 25. After 1 reduction, we're going to get to term 2. After 2 reductions, term 3, and so on, all the way up to after 5 reductions, we're going to be at term 6. So n has to equal 6. Well, now that we know this much, we can take our general equation and say T of n is 25 times 0.67 to the power of n minus 1. And T6 has to be 25 times 0.67 to the power of 6 minus 1, which is 5. And that's simply going to give me 3.375. If I round that, it's 3.4 centimeters after 5 reductions. Next one, your turn. Example 3. Let's slow this down. It says, in a geometric sequence, the third term is 54, and the sixth term is negative 1,458. Determine the values of term 1 and the common ratio, and list the first three terms of the sequence. So what I like to do is plug in what we already know. We know the third term is 54, so we don't know term 1 and term 2. Term 4 has got to be term 3 times the common ratio. Term 5 has to be term 3 times 2 times the common ratio. And term 6, which is negative 1,458, has to be term 3 times, not 3 times the common ratio, but the common ratio cubed. So there's my equation, that last box, which is term 3 times the common ratio cubed has to equal negative 1458. Now I know what term 3 is, so I can substitute term 3 with the number 54. And term 54 times r cubed has got to equal negative 1,458. Dividing both sides by 54 gives me r cubed, is negative 27. Now I can take the cubed root of r cubed and the cubed root of negative 27, and I'm going to get that r is equal to negative 3. Well, now that I know my common ratio, I can figure out the rest of these terms. I know, I'm putting a check mark by the r, that Tn is equal to T1 times r to the power of n minus 1. And I can say that the third term is 54. I'm going to use this to say that T3 has got to be term 54, which is term 1 to the power of n minus 1, which is 3 minus 1. So 54 is negative 3 to the power of 2, which is 9. Divide both sides by 9, and that'll leave me with term 1 being equal to 6. Now then, the first three terms are 6. 6 times negative 3 is negative 18, and negative 18 times negative 3 is positive 54. So it works. Those are the first three terms. Here we have your turn. You can stop it, then complete this. Moving on to the next example. We have applying geometric sequences. The modern piano has 88 keys. The frequency of the note ranges from A0, the lowest note at 27.5 Hertz, to C8, the highest note at 4,186 Hertz, 0.009 of course. The frequencies of these notes approximate a geometric sequence as you move up the keyboard. They want you first of all to determine the common ratio of the geometric sequence produced from the lowest key to the fourth key. Well, we can do that. We can say that the fork is going to be from 27.5 to 32.7. Just like we did in the last example, we're going to say term 1, term 2, term 3, and term 4. is term 1. The second term is term 1 times the common ratio. Term 1 times the common ratio squared. And the last term is term 1 times the common ratio cubed. And that's our equation. Term 1 times the common ratio cubed is going to be 32.7. I know term 1, so I can substitute T1 with 27.5. Subtract both sides by 27.5. That's going to leave me with r cubed is equal to 1.189. Take the cube root of both sides, and you're going to get r is equal to 1.0594, or approximately 1.06. For part B, it now asks us to use the lowest and highest frequencies to verify this common ratio. Well, if I say that the last term is equal to the first term times r to the power of n minus 1, I know all this information. My last term is the 88th term. It's 4186.009. This is equal to the first term, which is 27.5, times r to the power of n minus 1. Remember that n is 88, so this would be to the power of 87. Now, to get r by itself, I have to divide both sides by 27.5, and that leaves me with r to the power of 87 is equal to 4186.009 divided by 27.5. Now the next thing to do was take the 87th root of both sides. And that'll leave me with r equals, and that works out to be 1.0594, which we've verified is the exact same number that we just found. Again, this takes us to the end of our last example. We're going to work through this one by yourself. Here are the key ideas, and your assignment for this section is to do page 39, numbers 1 to 6. I'm sorry I didn't have time to work through the your turn questions. That's something that you can do on your own.